simple harmonic oscillator solving Newton's second law of motion. Let's say we have a spring of force constant K. We attach an object of mass m to this spring, everything resting on a smooth surface, no friction. At this point, the spring is relaxed. So let's say the object is at x equal to 0. I'm applying an external force to stretch the spring, such that now the object will be at some position A. A very soon will stand for amplitude. At this point, there is a force in the spring, a restoring force, given by Hooke's law. The force is negative Ka. If I let the object go, the object will start moving to the left. At any given point during its motion, the object will experience three forces: negative Kx, the normal force, and the force of gravity. The normal force and the force of gravity, they cancel out, and they will not play a role in this discussion. So the only force left acting on the object is negative Kx. If we write Newton's second law, this force is equal to mass times acceleration, or negative Kx is equal to m times d2x dt2, the acceleration being the second derivative of the position. If we rearrange the terms, we end up with an equation looking like this. And at this point, the term k over omega, we will label it as omega squared. It is just a label. So the equation has become d2x dt2 plus omega squared x is equal to 0. The solution to this equation is x as a function of time is a cosine omega t plus phi naught. Let's test to see if this is indeed a solution. The first derivative of this is negative omega a sine omega t plus phi naught. The second derivative, we bring another omega in front, so it's negative omega squared a cosine omega t plus phi naught. But a cosine omega t plus phi naught is precisely x. So this becomes negative omega squared x. If we plug this in back here, we see that indeed negative omega squared x plus omega squared x is equal to 0. So this is confirmed to be the solution. What does phi naught represent? It represents a phase constant, and that depends on the initial conditions. By initial conditions I mean, where was the object when I started the clock? If I start the clock when the object is at x is equal to a, as depicted in this picture here, then our equation becomes x of 0 is equal to a and at the same time is equal to a cosine 0 plus phi 0, which means cosine phi 0 is equal to 1 or phi 0 is equal to 0. So in this case, the equation is a cosine omega t is the solution. If at time equal to 0 the object is anywhere else, then phi 0 will not be equal to 0. And we'll have to calculate phi 0 based on the position of x at time is equal to 0. Now that we found the position, let's find the velocity and let's find the acceleration. If x of t is a cosine omega t plus phi 0, then v of t is dx dt, which is negative omega a sine of omega t plus phi 0. And the acceleration is a function of time. Let's take another derivative. So it will be negative omega squared a cosine of omega t plus phi 0. Or, if we recognize this term as x of t, will be negative omega squared x of t. We shouldn't be surprised by this expression, because if we look at the equation that we solved earlier, the acceleration d2x dt2 is precisely negative omega squared of x. So it makes perfect sense that taking these two derivatives, we end up with this expression for the acceleration as a function of time. How do we interpret these expressions? Well, that means x of t can take values between negative a and positive a, because of course cosine of omega t plus phi 0 cannot exceed 1 or minus 1. The velocity can take values between omega a and negative omega a. Same rules apply to sine. And the acceleration cannot exceed omega squared a and negative omega squared a. A, we call it amplitude, while omega a and omega squared a, they don't have special names. That's why we're going to call them maximum speed and maximum acceleration. But, of course, these are vectors, so every time we do that, we have to be careful if we are talking about the magnitude, which is the speed and acceleration respectively, or the direction. In that case, we have velocity and acceleration. We don't have a name for the acceleration vector. So let's see how this works in our problem. In the scenario depicted here, if at x equal to 0, the object is equal to a, so if at t equal to 0 the object was at the position a, here on the right hand side of the equilibrium position, then the velocity of the object at time equal to 0 is 0, and that is true because this is when we released it. And we see here that as the position here decreases, the velocity increases, and the negative sign indicates that it is moving to the left. as the cosine and sine are obviously out of phase. As the position increases on the other side, going towards negative a, the velocity will be still negative, but it will decrease towards 0 until the object stops on the other side and comes back. An important concept is t, the period of this oscillation, the object going back and forth. An easy way to find the period is like this. At t equal to 0, the object is at position A. Remember, we work with A x of t is equal to A cosine of omega t. At a time is equal to a quarter of a period, the object will be at 0. Why is that? I release the object here. In a quarter of a period it will be here. In another quarter of a period it will be here. In another quarter will be back. And after 4 quarters is back to where it started. So going from here to here will take the object a quarter of a period. So if I find this time and I multiply by 4, I find the period. So let's label this time t0. We know that this time will be equal to a quarter of a period. So if we find this time, we can find the period. Sorry, this is not x of 0, this is x of time t0. So let's see what happens. If x at t0 is equal to 0, that means a cosine of omega t0 is equal to 0, or cosine of omega t0 is equal to 0, which means that omega t0 is equal to pi over 2. Cosine of pi over 2 is equal to 0. So t0 from here is pi over 2 omega. And if we want to find the period, it would be 4 times this. So 4 t0, or 4 pi over 2 omega, or the period is 2 pi over omega. This is an expression that we saw when we studied uniform circular motion. That was the time it took an object to go around the circle once. At the time, we said that the time is equal to the angle swept divided by the angular speed. This is the definition of angular speed. Angle swept divided by time. So time was angle swept over angular speed. But if we want to call this time a period, that means the time it takes the object to complete 1 revolution, then the angle swept is 2 pi radians, and angular speed is omega. So 2 pi over omega. We'll see in a future video the fact that this is not a coincidence. The fact that we have the same relationship for simple harmonic motion and for circular motion, this is not a coincidence. So what is a simple harmonic motion? A simple harmonic motion is a motion for which we have a relationship like the one we saw here, a relationship that looks like d2x dt2 plus omega squared x is equal to 0. Anytime we have an equation like this, this is going to be called simple harmonic motion. And we will see later in this chapter that we'll encounter a similar equation for the simple pendulum and also for a physical pendulum, an object that oscillates with small oscillations. Both those motions, we'll study them separately. Both of those motions are simple harmonic motions.